A signal is a phenomenon that conveys information about a physical quantity. For example, the voltage across a resistor tells us about the current flowing through it. Temperature measurements over time form a signal. Even your voice is a signal, carrying information through air pressure variations. Mathematically, signals are described by functions. The name of the mathematical function and the signal can be used interchangeably. A system can be viewed as any process that transforms signals. It takes an input signal and produces an output signal. The relationship between input and output is defined by the system's transformation. For example, a loudspeaker is a system. It takes an electrical signal as input and produces a sound signal as output. We will draw systems as blocks with arrows showing the signal flow direction. Signals come in two basic forms: continuous time signals and discrete time signals. A continuous time signal is defined for every instant of time. The signal itself may have discontinuities, like a square wave, but the time variable is continuous. We denote continuous time signals as x of t. A discrete time signal, on the other hand, is defined only at specific time instants. We write it as x of n, where n is an integer index. Think of digital audio. It consists of samples taken at regular intervals. Now let us learn how to manipulate continuous time signals. There are three fundamental operations: time shifting, time scaling, and time reversal. These operations change when or how a signal appears along the time axis, but they do not change the shape of the signal itself. Understanding these operations is essential for analyzing signals and systems. Time shifting moves a signal left or right along the time axis. Given a signal x of t, the shifted signal x of t minus t0 is obtained by shifting the graph to the right by t0 units. Similarly, x of t plus t0 shifts the graph to the left by t0 units. The key rule is replace t with t minus t0 to shift right, or t plus t0 to shift left. Watch as this triangle signal slides along the time axis. Time scaling compresses or stretches a signal. Given x of t, the signal x of kt is obtained by dividing the time axis by k. If k is greater than 1, the signal is compressed. If k is between 0 and 1, it is stretched. Time reversal flips the signal about the vertical axis. The signal x of negative t is a mirror image of x of t. We can combine these. X of negative 2t means first compress by 2, then reverse. Or equivalently, reverse first, then compress. Let us work through an example. Consider a triangle signal x of t that rises from 0 to 1 between t equals 0 and t equals 1, then falls back to 0 at t equals 2. Shifting right by 3 gives x of t minus 3. The same triangle now spans from 3 to 5. Compressing by 2 gives x of 2t. The triangle spans from 0 to 1, twice as narrow. Reversing gives x of negative t. The triangle is mirrored to span from negative 2 to 0. Let us review the key signal manipulation rules. Time shifting. X of t minus t0 shifts right by t0. Time scaling. X of kt divides the time axis by k. Time reversal. X of negative t mirrors about the origin. In the next lesson, we will combine these operations to handle transformations like x of at plus b, which involve both shifting and scaling together.